Good evening to everyone. I'm Luciano Strambini, researcher of the Institute of Electronics and Information Engineering and Telecommunication. And I'm here instead of our director that cannot be present due to unavoidable commitments. So in his place, I'm introducing the series of seminars called Tuesday's Meetings. I want to thank Professor Simon Burton of University of York to be here with his contribution to the webinar. And before to leave the floor to my colleague Maurizio Mongelli that will introduce you the speaker, I want only to remember to everyone that the seminar will be recorded and that at the next days it will be available on the YouTube channel of our institute. And so for every kind of privacy question, remember to, if you don't want to be recording the video, to turn off your camera and or microphone. So I don't want to spend any other time, and I want to leave the floor to Maurizio. Thank you very much to the speaker and to all the people there.
Hey, thank you, Lucanos. Well, just a few words. Welcome to Simon and welcome to all the people in there. We have seen some participants are coming as well. And well, informally speaking, I would say I'm very glad to have here Simon, one of the most prominent researchers in safe AI and inherent certification and standardization processes. Actually, the University of York did one of the first, I would say, regulation plan on AI over a decade ago by anticipating the European AI Act on several issues, mainly technological, but also ethics. And so the topic of today, safe AI, is of great interest. As you know, AI or automatic procedures in many fields are becoming spread, and human beings are becoming either enthusiastic or skeptical on the technology. And so there is the need to scientifically investigate how and when an autonomous decision is safe and can be applied in practice. And so that's why, Simon, you are here, and we are very curious about your presentation. More formally speaking, just the canonical official short bio, Professor Simon Burton holds the chair of System Safety at the University of York, UK. He graduated in computer science at the University of York in 1996, where he also achieved his PhD on the topic of verification of safety critical software in 2001. Simon has worked in several critical industries, including 20 years as a manager in automotive companies. During this time, he managed research and development projects and led consulting, engineer services, product and research organization. Simon more recently was a scientific director for the safety assurance at the Fraunhofer Institute for Cognitive Systems until December 2023. And he is now convener of the ISO working group on road vehicle safety and AI, and currently leads the development of the standard ISO Pass 188 safety and AI, scheduled for release in 2024. And I think this would be one of your most important topic of today. So thank you again, Simon. The stage is yours. I take a note, I look at the chat for if someone would like to just write a question, and also please raise your hand and I would leave, try to manage the question and answer at the end of the presentation.
Okay.
Please, Simon.
Thank you very much, Maurizio. Hopefully you can see my screen.
Yeah.
Excellent. Well, thanks very much for the invitation to talk today. And what I'm going to do in my talk is give you an overview of some of the challenges associated with applying AI in road vehicle functions, let you know how much progress we've made in standards on this topic, but also talk a little bit about some of the unanswered questions, and especially some of the unanswered questions that I'm looking at in my current research. So let's start off with a motivating example. Unfortunately, in the field of safety, most of our use cases and examples don't have a happy ending. This one doesn't either. So what you can see here on the screen is information from the National Transportation Safety Board accident analysis of an accident that happened between a prototypical automated driving vehicle from the company Uber and a pedestrian you can see here in the middle of the screen. So on the right-hand side of this screen, you can see a log of what happened. So the accident investigators reconstructed the last seconds before the crash. And what you can see highlighted in red here is the fact that as the vehicle was approaching this pedestrian pushing the bicycle across the road, the vehicle was constantly reclassifying the pedestrian as a different type of object. So initially the radar thought the pedestrian was a vehicle, and then the LiDAR saw it, wasn't quite sure how to classify the object, and then it moved forwards and forwards, and towards the end, the object was classified as a bicycle, but because each time the object had been reclassified, the trajectory was lost. The vehicle wasn't tracking the fact that this object was actually moving across the road and instead of in the same line of the traffic. So it led to an accident. So a tragic ending to a test drive. At the same time, you have to acknowledge that there was a test driver in the vehicle who was responsible for actually monitoring the performance of the vehicle. But that test driver was distracted by her mobile phone. At the time, she'd got so used to the vehicle working correctly that she just stopped monitoring the vehicle. So let's have a look at the time of these systems being developed back 5 to 10 years ago. What type of safety standards we had? Well, the most famous safety standard in the automotive industry is 26262, which is the ISO standard for functional safety. And functional safety is defined as the absence of unreasonable risk due to hazards caused by malfunctioning behavior of the electrical and or electronic systems. Well, what do we mean by malfunctioning behavior? Here in this standard, we mean errors and malfunctions caused by either random hardware faults or systematic faults, where systematic faults here are seen as things like software bugs as well. Well, that really wasn't what was going on in that example. The type of problems the vehicle had were much more subtle than that. The ISO 26262 standard does also highlight the need for good safety management processes. And one of the things the accident report highlighted was actually that the safety management procedures weren't properly in place in the company. So that's definitely something that should have been picked up upon. But these other type of issues wouldn't really be covered by this standard. So let's have a look at the type of problems we do have with automated driving vehicles in working in these types of open context environments. Well, first of all, these vehicles have to operate in an environment that is inherently complex and very unpredictable. The pedestrian that was hit by the vehicle shouldn't actually have been crossing at that part of the road, but the way the road layout was made it look like it was a pedestrian crossing area. And obviously all sorts of things happen in real life that we just cannot predict. At the same time, we try to make sense of this very complex environment through a set of sensors which may be inherently noisy or may have limited fields of view. So we're trying to make sense of a very complex environment through a set of very limited sensors. So a few years ago, this is where we thought, well, hooray, AI to the rescue. Machine learning can deal with very complex inputs data. It can deal with unstructured, noisy data. Let's use machine learning to help fix these problems. Well, unfortunately, we see that machine learning itself is an inherently uncertain technology, and that's something we'll come back to in a slide or two. So as a reaction to these types of use cases, partially automated driving, for example, a new type of standard was created, so 21448, which defines safety of the intended functionality. So this is a slightly different definition of safety risk, defined as the absence of unreasonable risk due to hazards resulting from functional insufficiencies of the intended functionality or by reasonably foreseeable misuse by road users. So what you can see here, the standard deliberately avoids using the term malfunction. So it's not about when the system is broken, it's when the system is just not good enough to be safe for its operating environment. And these functional insufficiencies that can lead to hazardous behavior or can also lead to the inability to prevent misuse of the system, and the accident was actually a combination of both. These insufficiencies can be caused by both insufficiencies in the specification. In other words, the system wasn't specified properly, or insufficiencies in the system itself, so-called performance insufficiencies. The system just was not performant enough, it just was not good enough to achieve its functionality that was intended. And these insufficiencies tend to manifest themselves as residual faults or residual problems in the system that are uncovered under certain conditions, so-called triggering conditions. So as I mentioned, one of the enablers for the automated driving hype we've had over the last few years is artificial intelligence and machine learning in particular. So this standard mentions AI and machine learning, but doesn't give any concrete guidance. So the next step was then to look at how this standard could be applied for AI and machine learning based components. So one of the things we did, we looked at the definitions in this SOTIF standard and looked at how to interpret them to AI and machine learning. Well, let's start off with this topic of insufficiencies of the specification. Obviously, we tend to use machine learning and AI often in conditions where we don't have a complete algorithmic specification of the function. But what that means is it's very hard to determine what it means to have a complete specification of the function. And especially when we're dealing in a very complex environment, how to ensure that we've thought about all possible events, critical events, but maybe very rare in practice. But also these environments maybe shift and change over time as well. And there's a real difficulty in coming from some understanding of the task and the environment and breaking that down into sort of technical specifications at the machine learning component level, including defining a set of KPIs and metrics that can be used to measure conformance to the requirements. And of course, in many senses, the data itself we use to train the system is the actual specification. how do we then demonstrate that the data is really a sufficient representation of our intended functionality? Then if we look at the models themselves, once they're trained, the term performance insufficiencies from the standard maps quite nicely to the types of problems we have here. So these trained models inevitably will always have some residual errors. And this might be due to bias in the training data, a lack of generalization, or lack of robustness to small changes in the inputs. These residual errors are just a byproduct of the fact that actually machine learning is just an optimization game, right? It's trying to fit a set of parameters to the training data and approximate the target function as represented in the training data. And a lot of this has got to do with potential mismatch between the complexity of the task we're trying to train the model on, whether or not that complexity is represented in the data we're using, and also the potential expressiveness of the models themselves in terms of the number of parameters they have, training function, loss functions, etc. So one of the properties we see of machine learning functions is it's very hard to interpret when they are going to fail. They don't necessarily fail in nice semantic classes that we can identify with certain sets of input conditions. They tend to fail in what looks like a random way, but of course their execution is actually deterministic. So I was asked a few years ago to build upon these concepts and to extend the standards in automotive with a new standard, which was ISO PAS 8800, which is a standard that's now been finished, been written, and will be released in the next few months. So the type of standard we're talking about here is what I would call a process-oriented standard. So it defines a safety life cycle of how to develop an AI-based vehicle function in a safe manner. It contains only a few very high-level requirements for each life cycle phase, because we don't want to be specific to a particular AI or ML technology. And we don't also want to be specific to particular applications, such as automated driving. We want to cover all possible AI-based technologies for all possible vehicle functions. However, a lot of the guidance in the standard and the examples used focus on machine learning for tasks such as perception and task planning as well. But they shouldn't necessarily be seen as promoting very specific solutions. The standard focuses on the AI model itself in terms of how to specify, optimize, and test the AI models, but it also considers the wider context in terms of pre and post processing that might need to be performed such that this model can actually execute safely. And another aspect of the standard is we look at through life assurance. So in other words, how to maintain safety of the AI-based system during operation. And that obviously requires a lot of interaction with the system level as well, with at the vehicle level. So to give you an idea of how these standards fit together then, we have 26262 and 21448, so functional safety and SOTIF, which would be applied at a vehicle system level or vehicle function system level, such as a traffic jam assist functionality, where some of that system may require the use of AI or machine learning, such as the perception task. And that perception task then would then be encapsulated in what we call a AI system, including the trained model, pre and post processing as well around that. And this part of the system still needs to be implemented according to functional safety guidelines. In other words, it still needs to be ensured that we don't have any random hardware failures that could lead to safety issues or silly software bugs that could lead to safety issues, but the standard extends these concepts with some others as well, which are much more closely related to the topic of safety of the intended functionality. In terms of the safety life cycle, yes, there's a V model in the middle of it because the automotive industry likes its V model and has been using that for years. But if you look closely at the safety life cycle, and in the published version of the standard, it will look slightly different to this. This is more of a simplification, but there's lots of iterations that are being described here. So it's an inherently iterative approach to achieving safety as the system is being developed. So we have at the core type of ML ops iterative approach to training the function, testing the function, analyzing how it can be improved, getting more data and repeating that process. But it could be that as part of that iterations, we may decide that actually the safety requirements that have been allocated to our function maybe can't be achieved. So they may need to be renegotiated with the system level, which is why the safety lifecycle has a number of different points at which the development of the AI part of the system, it needs to be negotiated within the overall vehicle system context as well. And these iterations continue until sufficient confidence in the assurance argument is created, and then the vehicle can be released for operation. And then during operation, the assurance argument is continually reevaluated to see, well, has the environment changed? Have I discovered issues that were somehow hidden during development? What type of updates do I need? Do I need to update the AI system itself, or is it more at the system level that I need to take some actions? So one of the parts of the standard that really includes some interesting guidance, because this is maybe slightly different to classic software development, is the fact that the safety requirements we allocate to these systems from the SOTIF level, they tend to include some type of quantitative acceptance criteria on our safety requirements. So let's say we have a safety requirement that says correctly classify construction signs for any given image. And there might be some acceptance criteria associated with that that says, well, it's unacceptable to misdetect more than 10 to the minus 4 classification signs per event. And what the standard tells you to do is to start at that level and then refine these requirements into a set of measurable properties on the AI and machine learning functions, such as generalization, robustness properties, bias, etc. And for each of these properties, we need to also derive some target values and metrics by which we can define those properties and see whether they're being met. And that's a very non-trivial task. And the standard gives some guidance here by presenting a set of safety-related properties that can be used as keywords as part of this refinement, but it still needs to be demonstrated by the developer of the system why certain properties were being used to derive the safety requirements, why certain target values were being set for these derived requirements as well. And another thing that a standard tells you to do, the standard accepts that in some cases, not all of the requirements can be met all of the time. So the standard tells you to characterize the limitations of the AI system and pass that information back to the vehicle system level so that compensatory measures can be made at the vehicle system level. For example, if you know that your camera-based detection system doesn't work very well in the dark, see my very first slide, then maybe you need to rely on your radar or LiDAR better. Actually, in the example from the first slide, you also saw that the radar and LiDAR also didn't work very well, but that was more to do with the design of the system. But it's telling you to acknowledge where the weaknesses are in the system and make use of that to actually build a more robust and safer system. To do so, the standard allows you to use different architectural elements to encapsulate and wrap your machine learning models using things such as redundancy, checkers, etc. And if you can argue the effectiveness of these additional modules in your system, then that might help to reduce some of the absolute performance requirements on the machine learning models itself. But to do so, you do need to know what type of errors you should expect and how effective these additional measures are at actually detecting and mitigating against these errors. Another innovation in the standard is actually recognizing that data in the development and test of these systems is actually a first-class citizen for safety. So in other words, data is safety relevant, training and test data. So the standard describes a data lifecycle that looks like a typical software lifecycle. In other words, we expect safety requirements to be defined on the data sets. We expect the data sets to be designed explicitly in order to meet those requirements. We do safety analysis on the data sets to see what type of problems in the data set could lead to safety issues and what type of measures could we add to mitigate against those. Verification of the data sets is important. Validation of the data sets. Are the data sets really representing the intended functionality we're looking at? And as part of the safety analysis approach of these data sets, we also define in the standard a set of keywords, again, typical properties of the data you might want to consider when designing the data sets and looking for potential safety related problems with the data. So these are things such as a lack of coverage of the input space. So maybe forgetting to consider that pedestrians may also be pushing bicycles and therefore may appear differently. Distribution of input events in your training data against the real world. So maybe input events that might be very rare in your training sets may occur more often in the real world, etc. Errors in the labeling of the data and the ground truth definition of the data, etc. So again, the standard gives you some guidance as to how to perform these types of analyses. We also talk in the standard about the difficulties of transferring traditional software testing techniques to AI and ML, particularly because of the opaque nature of the AI models and machine learning models, and therefore the increased reliance on statistical testing and other types of techniques such as search-based testing. We reflect upon the role of virtual testing and physical testing in these types of systems, and we also look at the difficulties associated with safety analysis. And one of the problems of safety analysis we have with these types of systems is it's very hard to model causal relationships between the types of errors that these systems make and what the fault was that led to those errors. So it could be a combination of data issues, it could be a combination of the type of model you use in, combination of the way your input space was defined or your operating domain was defined as well. So what the standard does is it says when you identify a potential cause for an error and you propose a measure to remove that cause of error, then you also have to justify and demonstrate that that measure was really effective, that you really have less errors of that type as a result. And one last highlight of the standard is the fact that we acknowledge that there is no best practice or state-of-the-art one solution fits all recipe for designing safe AI-based systems, and there won't be in future. It'll always be very dependent on the application, and it will always be very dependent on the technologies used. So what the standard asks you to do is, as well as obviously implementing the requirements of the standard, to create a system-specific assurance argument that explains to a potential certifier or product liability judge why you believe that your system was safe. And in the annex of the standard, we use the GSN notation, which you can see here, to explain how such an argument can be justified, but it's not a requirement. It's just an example of how such an argument can be documented. What we also ask you to do is to justify why you believe that argument as well. It's not good enough just to say, well, I did this and that, and therefore I'm safe. You have to critically reflect on that argument and say, where would be the potential defeaters, where would be the potential problems that could undermine this argument as well, to make it more robust as well. So last point about the standard, and then I'll talk a little bit about future work. So it's important to understand that the safety standards I introduced, although they're now defined as a package and hang together quite nicely, they should only be seen as one part of a more complex landscape of standards and regulations. We have a lot of function-specific standards, especially in the area of automated driving systems, which are describing different use cases, test scenarios, etc. And these functionality-specific standards need to be implemented and interpreted within the context of our safety standards. At the same time, there's masses and masses and masses of standards being developed at the moment from all possible organizations, from ISO through to IEEE, SAE, BSI, IEC, DIN, etc., etc. And a lot of standards being defined and developed for AI-specific issues, which may be generic and independent of the application they're being used in. So there might be standards for explainable AI, standards for measuring robustness of machine learning-based functions, etc., etc. And these standards could be used to actually help us implement the requirements from our vehicle-specific standards as well. And at the same time, the regulatory landscape is developing as well. So we have some vehicle standards and regulations, so automated driving regulations that are coming into place, for example, from the UN ECE working groups, as well as the technology-specific regulations such as the EU AI Act. And these standards, or these regulations, sorry, are already referring to safety standards and will do so more so in the future. But also, if we look at the EU AI Act, they're also asking for new standards to be developed as well. So it's a very complex landscape, and for anybody developing these types of systems, they need to be aware that it's not just one standard that needs to be implemented, it's a whole family of standards, and there needs to be much more guidance and support provided for developers of these systems in how to actually interpret these standards and come up with an efficient development process that covers all of these things. So we've got a bunch of standards that are telling us how to build safe AI-based systems. Are we there yet? Well, depending on how you look at it, fortunately or unfortunately, no, we're not quite there yet. I say fortunately because I'm a researcher, so I like open questions, and that's what I'm working on at the moment. So to structure the research, I started in this area. I thought about, well, what makes a good and effective assurance argument? And actually, Natarajan Shankar in his keynote last year at SafeComp actually gave a very nice talk where he highlighted 4 principles of effective assurance arguments. And we can use that to see, well, how far are we away from a good, convincing assurance argument from AI? Well, he says, first of all, we need to have a clear definition of the safety claim to be demonstrated. Well, we know that there's difficulties in formulating safety requirements at a system level as measurable properties of the ML models, as well as coming up with the right set of safety requirements in the first place. for these types of systems. That's one area we need to look at. He also mentioned we need an assurance-driven workflow for continually and incrementally capturing evidence during development and operation. That's good. That's what we've got already in the standards. So that's covered. These arguments need to be based on rigorous models of the system and the context. Well, the system itself here, including very opaque machine learning models with lack of explainability, that's not always a good way, a starting point to argue why you think your system will always work correctly. So that's something we need to work on. But also we often have an incomplete definition of the input space and the environment we're working in as well. So the models of the system and its context are often insufficient or incomplete in our domain. And lastly, Natarajan talked about using evidence and arguments that can be easily refuted or believed. So in other words, if I present an argument and supporting evidence to you and say, I believe my system is safe because look, here I did this, you should be able to easily say, yes, I believe you, no problem, or no, you're talking rubbish. It should be obvious whether or not this argument is convincing or not. And that's something I want to look at now in the next couple of slides. That's one of the areas I'm doing research on. Because a lot of the machine learning community is spending a lot of time developing metrics and demonstrating how their special optimization of their model can improve this metric from 98.1 to 98.2. It doesn't tell us what are the units they're measuring in and how this metric really relates to safety or other important issues as well, and whether or not we should even trust this measurement as well. And these are the types of questions we need to ask as safety engineers. So to formulate the way the research problem, I use this equation on the right, which you don't have to understand in detail, but basically what it's saying is that on the right-hand side, there is the actual safety risk you will encounter in the field. So how often will something bad happen in the field, or conversely, how often will everything go okay? And on the left-hand side is our means of measuring that and predicting that level of safety. In other words, typically we do testing and we take a finite number of test samples and we apply those test samples to our system or one part of our system. We measure certain properties of the system and then we come up with some sort of score for that property. And the question is, that estimation we're making, is that really equivalent to the actual level of safety risk we'll have in the field? And for the reasons I mentioned in this presentation, I think there can be a big gap between the two, between our estimation of safety and the actual safety. And I call that gap the assurance uncertainty. So in other words, uncertainty about the estimations we're making about safety of the system really being accurate and true. So based on that, we've defined an approach of how to incorporate machine learning metrics into a safety assurance argument. And effectively, we start off by looking at certain safety requirements, collecting some evidence to support those safety requirements and safety claims, and then think about how much uncertainty is there in that evidence from a statistical perspective. If we have just a few number of tests, obviously we will have much greater uncertainty than we have a lot of tests. But also, it's not only the number of tests that will impact how accurate our safety estimate is. If we have the wrong tests that are measuring the wrong properties, then we also can't trust our estimations as well. So if our tests don't have an adequate coverage of the input space, they miss out critical semantic classes of the input space, then we'll also come up with the wrong evidence, for example. or if our model doesn't have a certain level of robustness or calibration to it, then it might also skew our test results and our estimations as well. So we have to think about what type of properties of our system, as well as our test data, could undermine our evidence as well. And then we use that information and knowledge to actually adjust our estimates to model the amount of uncertainty we have in our estimates, and that will allow us to make much more conservative judgments, much more realistic adjustments to our estimations to find out what is the sort of lower bound of the actual level of safety we should expect. So we came up with a method of applying statistical techniques based on subjective logic to manipulate our evidence based on an analysis of what could undermine our safety arguments to actually model the amount of uncertainty we have in the end in our tests. And the way that works is basically we'd start off collecting evidence. We'd think about what could be the potential defeaters to that evidence, what could undermine that evidence. We would then use that to model the uncertainty in our evidence so that you see the uncertainty spread in our estimations is getting bigger as we go up the argument here. It also allows us to combine evidence as well. So if we have two completely independent sources of evidence come into the same conclusion, then we can combine those again and actually be more confident in our estimates again. So the approach we're taking here is to look at how we can model some of these more quantitative and statistical aspects of machine learning functions and put some of the machine learning metrics that are often used within this overall context as well. And you can find some of the preliminary results in some of the papers I've mentioned here. We've just had another couple of papers accepted as well. So we're going to be continue in building on this piece of work. And this will give us more confidence in the safety assurance arguments we have for machine learning. So that's just one area of work that needs more research. And just to come up and wrap up the talk now to have time for discussions, more research is needed in a number of different areas. One of them is looking at how to derive the right set of safety requirements on our machine learning functions in the first place. How do we go from very high level safety requirements to some measurable properties, and then how to measure those properties in an accurate way. We need to use evidence that goes beyond simple metrics based on arbitrary test data, but we need a more rigorous approach to statistical reasoning based on quantitative evidence. And what I just gave you as a slight sneak peek preview on the last two slides shows us the type of direction we could go in to improve the statistical rigor of our evidence. We need to continue to reduce the uncertainty in the integrity and validity of the evidence as well. So we need to look at thinking about coming up with better testing techniques, but also maybe making use of formal verification where we can for very well-bounded properties such as robustness, and looking at how we can scale these approaches more to reduce the amount of uncertainty we have in our evidence. And lastly, there will always be some errors left over. So we need to look at high integrity safety measures at the architectural level to mitigate against residual errors in the model. One of the problems we have there is the more complex the task gets, the harder it is to define a safe state for the system. So we often have a balance between safety risk and utility, where actually to achieve safety, we might have to have very conservative architectural measures that if we're not sure about anything, we just turn the whole system off and never leave the garage. So actually finding the right balance between utility, permissiveness of these safety wrappers and architectural measures, and the residual errors is actually quite a challenging task. So to summarize, we've got a set of initial standards that will allow us to introduce AI into a safety level, safety relevant context in automotive in future. But the ability to provide a convincing argument of safety is going to be dependent on the complexity of the environment, the task itself, as well as the resulting models. So there may be some more simple applications that we can deal with current state of the art quite nicely, and we can fulfill the standards for these simple applications. There may be more complex applications where we just don't have the state of the art at the moment. So acknowledging and managing the resulting uncertainties from this complexity is really essential to make a convincing safety argument. And the more complex the system is, the harder it is to trust the argument itself. And it may be that we get to a point where we try to release a system where we do not have a perfect safety argument for, in which case we need to then start to introduce more measures related to resilience in the system, to allow us to release systems that we don't have a complete argument for always working under a certain set of conditions, but we argue that the system nevertheless remains safe, even in the case of errors, even in the case of it operating outside of its originally intended set of conditions. An anti-fragile system in this context would mean that this system would learn from that exposure to difficult conditions and actually get safer over time. So there's a lot of research to do. We've made a lot of progress, and I'm now looking forward to your questions and the discussion. Thank you very much.
Thank you, Simon. Thank you very much for the overview of the standards, SOTIF, and the last issues, open issues in the technical and scientific perspective. Well, I know some people in the audience may have questions, so don't be shy and just raise your hand in case, or put the question on the chat at any time. In the meanwhile, I can just to let the ball rolling. I have a question about, I appreciated a lot, in particular when you actually mentioned my viewpoint on such a sort of overlapping of standards, the ISO, the IEEE, the different inside ISO, SOTIF, and we recently had some connection with the Safe AI standard in the NATO environment as well, touching explainability and robustness as well. Do you foresee any plan of ways to overcome limitations from different angles over the same issues and problems? I mean, is there a kind of regulation and interception between the different committees?
Yeah, so it's we try our best. Let's put it this way. So within the ISO committee I'm responsible for, we have formal liaison with other ISO committees. So we have a formal liaison with the AI committee that allows us to make sure that all of the ISO standards are complementary and don't overlap too much and build upon each other. We also have liaisons with other standardization organizations such as IEEE, SAE, etc. But that's quite difficult because everybody goes at their own speed. And obviously, every standardization organization at the moment is in a real rush to bring out some standards, because we really need standards and we can't create them quick enough. So ISO is a very large organization, and ISO is very good at achieving international consensus. So an ISO safety standard is really supported by the entire world. And in the automotive area, all of the automotive companies know that's the standard to follow. Whereas, but that takes a little bit more time, right? So the other standardization organizations say, well, we can do it a little bit quicker, and maybe they push the state of the art forwards quicker. And we at ISO need to be aware of that and try to bring it into our standards as much as possible. And we do try to collaborate. What you do see sometimes is just out of randomness and lack of awareness that, two initiatives start in parallel and end up doing the same thing. That's in the nature of the complexity of the topic, I think, and it's very hard to prevent, but we do our best, and there is certainly interactions here. And I recently wrote a report about the complexity of this landscape as well, which we publish soon. So keep an eye on my LinkedIn channel for that, and that will help people navigate a little bit through these standards.
Yeah. And we will let you know if we can organize another kind of presentation from some people inside the NATO working group. Yeah. And so, as a subsequent step of your reasoning, I have in mind the European Act, just released, and I think all of us believe Europe as the unique understanding of human, not in the loop, at the center of the technology, so different from US, China, and all the rest. So the ethical issue is important, but that's my specific feeling. I have heard about several R&D of many companies in Europe are migrating to the US in order to have their own research without the pressure of, let me be sincere, 133 recitals from the law, 13 attachment. And so in front of your discussion about the coordination of the standards, which is the possible good relation between the European Act when the European Act releases to the other standards, the final certification of...
So I think the part of the problem is, can you still hear me okay? Something's
Yeah.
Okay. Part of the problem, if those companies that move to other countries to do their development, they may still want to sell their products in Europe, and then it's going to have to still be qualified according to the Act. The AI Act includes a number of standardization requests, so it also asks for standardization to support compliance. From an automotive perspective, for example, there is some clarity needed because the automotive industry is already safety regulated, and the EU Act says, well, this doesn't apply to the safety regulated industries, but it also says, oh, but by the way, you should somehow keep an eye on this or think about adapting your regulations in future. But of course, for any other use of AI in the automotive context, if I'm using AI to plan my trip home or whatever, then the AI Act also applies. So it is hard to avoid. When interpreting the AI Act, I think it's important to understand what's meant by high-risk systems, because that's where a lot of the requirements are applied. And those high-risk systems and the types of requirements applied in those high-risk systems aren't really that different to the way we develop safety-critical software-based systems anyway. So what is needed now is an analysis of the AI Act, an analysis of the way we develop safety-critical systems or high-risk systems, the AI Act would call it, within the different industries to see what is the true difference. Maybe they're asking us to do something we do already, and then it's not so bad, right? It's if they're asking us something that we've never done before and doesn't even make any sense in our industry for our types of systems, then obviously it's more of an issue. So one of the things that we're doing in Germany, but I also know that in Italy and in France, similar discussions have been started, is to actually look at the Act in more detail and say, well, how does this really relate at a sort of semantic level to the way we currently develop our systems and the type of guidance we already have in standards such as ISO 8800, so we can work out what that difference is and see whether it's really a problem or not, or whether we can say, actually, it's pretty much equivalent to what we do already.
Yeah. And who is in charge to state this?
Well, this is where each national delegation are doing their own work, and there's normally big companies involved with very highly paid lawyers who also give their opinions as well. And what I'm trying to do at the international level is bring together these opinions so we can, it's like, double check, have the Italian group come to a similar opinion as the French group, and what's missing, and maybe the Germans have a different opinion as well. So we're bringing together those experiences to really try to understand the implications as fully as possible. And at the same time, there's other parts of the world outside of the EU that are doing similar things as well. So those countries, whether it's US or China, also doing their own analyses, and it's going to be interesting to compare as well. So I think, more work is needed to do that analysis.
Yeah, thank you. Yeah, that's interesting. Is there any question that may raise from the audience? Gilberto, please, welcome. You can open the microphone, and the camera if you like.
We can hear you, yeah.
Oh, okay. So Gilberto Burgio from Collins Aerospace. So we have similar problems, of course. And so the question is that to have, so if you have models more under control, so you know what the model are doing. Actually, I'm used to engineer things in this way. So trying to understand, I know what in the model is because I developed it, right? So it's not that there is a computation chain that I'm not aware of what it is. Then in that case, I can reduce the number of tests to have an overall acceptance from a community that the system is safe, okay? If I'm not aware, if I have low knowledge of a model, then I'm kind of blind from a certain point of view, and then I need to increase the number of tests, okay?
Yep.
Now, we are saying in the case of artificial intelligence, we are kind of less aware of what's inside the model. Then we need to increase the number of tests. But and actually, right, we can state some numbers, as you said as well in your presentation, right? So, and then it's more difficult than traditional system because we try to specify with maybe test data, right? The environment where the system is working, right? And this is one side. The other side is how can our model fit that test data, right? And this is another variability that before we didn't have, right? How far, and then we can then find out numbers, whatever, all this test data you need to fit with the confidence of a certain number, right? But all this has a cost, and the cost is up to the producer of the system, right? So we didn't talk about this. How far are we? Because anyway, we can say, well, you need to increase enormously the number of tests, but then the system won't be any more feasible from a cost point of view, and no one will produce it, right?
Yeah.
How far are we, right, with the automotive community? And Renault.
Please, Gilberto, increase the microphone. We cannot hear you anymore.
Oh. Okay. Did you?
Yeah,
that's better. Yeah, that's better. Yeah. So I think I got the question. How far are we here? And you mentioned the topic of this potentially infinite cost because we have to just do more and more tests.
Exactly.
And, so you're absolutely right. This is part of the crux of the problem from a computer science perspective. Actually, because in classic safety critical software development, we achieve a prior probability of the software being correct by using programming guidelines, well-structured architectures, doing code reviews, doing static code analysis of certain properties. So we're restricting the possibility of failure during the development. So that means we can reduce the amount of tests we do. And because formally what it means is that we can make certain assumptions when we're performing our tests, so that we can do what we call the uniformity hypothesis assumption, where we say, well, actually, we only need to do selected test data points, and we can assume that in between those data points, the system will behave in a similar manner. And we can't do that if we have a completely black box system that seems to work in a purely stochastic manner. So that's basically the core of the no free lunch problem we have in safety critical applications of machine learning, because it's okay for a lot of systems to just reach 90% performance. That's way better than we would have done using non-AI based technologies. And hey, that's great, aren't we clever? For safety critical systems where we need a proof or a strong argument that we're going to be 99.99999% safe or whatever, we can't do that. So I think part of the challenge is trying to find the set of properties that we can impose during the development of the ML-based system, and properties we can measure of the system that will allow us to move away from this sort of infinite testing problem. So these are things like defining the properties that the training data will need to have to ensure that we have a certain amount of robustness in the function. Defining how to achieve prediction certainty. So in other words, there's sort of certain stability in the outputs of the function as well to move on. And sometimes that might mean we have to limit the complexity of the function we're trying to implement. So if we're using linear regression for some fairly simple task, that we might be able to do that quite easily. If we're using deep neural networks or generative AI for very complex tasks, it may be very difficult to work out how to do those trade-offs with design measures and then finding the right combination of testing techniques so that we don't have to just test every possible input that we'll experience in the field. But that's exactly the challenge we have, and it's trying to come up with that appropriate combination for any specific application and technology. That's part of the challenge. So I agree.
Thank you.
Yes, that's interesting as well. Thanks, Gilberto. Spencer, please, if you raise your hand, you're welcome.
Yeah, let me see if oh, there we go.
Yeah, hi, Spencer.
Thanks, Simon. That was good talk. So I guess the question that I have, which I guess is putting you on the spot in the sense that I don't really know if anybody has the right answer at this point, but I'll pick your brain on it, is how do we detect automatically the uncertainty in either the operational factors or the operating environment or insufficient training data real time while a machine learning model is being deployed, right? Because you've got your autonomous vehicle, it's running, and maybe for whatever reason people's fashion choices change, or the types of streets that it's driving in aren't identical to what it was being trained on. So real time, how do we know, okay, I'm no longer certain about, I'm in the right with what I'm thinking. So then we can maybe move to a degraded performance level. So that cognitive switch, you need a detection mechanism for. So I'd be interested to hear your thoughts on that.
Yeah, there's been a lot of research in this area for the last few years, and I think that I examined 3 PhDs last year, all on the topic of out of distribution detection, all taking very different approaches, all with fairly, they're very well written PhDs, worthy of passing a PhD, but despite using different approaches, finding the same limitations, right? Because for AI-based systems that work in the subsymbolic space, so in other words, the representation, internal representation within the model does not map to any type of semantic representation directly that we would work with. We're looking for sort of anecdotal evidence that somehow the model doesn't know what it's talking about, or is somehow confused. And so it's very indirect, so it's very difficult. There are different approaches that have been applied. Things such as ensemble learning is interesting. In other words, basically the way these models work, you start off with a random set of parameters, train the parameters according to the training data, and then you get some results. And if the assumption is, if the models see something that they haven't been trained for, they will react in some way, but they'll react in sort of a random way based on their original random initialization of the parameters. And if you ask different models with differently randomly selected initial values for the parameters to look at the same input, then they're likely to come up with different outputs. And you can say, well, there's some disagreement here. And that's just one way in which ensembles work, and there's other ways as well. But trying to use that inherent uncertainty in the way the models do their processing to actually see when they disagree, that's maybe a situation that is really truly out of scope. It's not just a generalization error in one model, but it's really an issue. There is some work, but it's been very inconclusive, and in the end it comes down to a type of conditional probability where actually you have to have the probability of being out of your distribution, whatever that means for your trained model. The probability of your model then actually coming to the wrong conclusion, because often they can extrapolate and nevertheless come up with the right answers, even if they're in a situation they haven't seen before. That's one of the reasons we do this. And then the probability that these out of distribution detection systems will also detect properly when you're actually out of distribution, and also won't give you false positives all the time as well.
Yeah.
So all of these things have to come together for this whole idea to work. And often people sort of overlook that. You know, they just focus on one part and they don't think about, well, how often am I really out of distribution? How often am I out of distribution? But hey, okay, I'm still coming up with the right answers, right? And
yeah, exactly.
Actually adding these measures often introduces then more errors, because you're creating, you're either saying, well, I think I'm out of distribution when you're not, or you're saying I'm out of distribution and you're going into some safe state when the model would have come up with the right answer anyway. And it's so it's still a very open issue there. And yeah, I think we'll be optimizing around the edges for a long time before deciding that actually we need a fundamentally different approach.
Yeah, of course.
That's my personal opinion. It's
Yeah, great. Is there any other hand to raise? Any more question or comment from the audience? Please, Lucanos, tell us if we are over the canonical time range, or do we still have time?
No, don't worry. If we are using the time of the speaker, so if he was available, we can have time for other questions. But I don't want to use much time of the time that he dedicated to our event. So I think that for other question is possible, but okay, I
let's
leave you the
one more question. I've still got some things to do today, but I can see one hand raised at least. So let's have one more question.
Okay, Gilberto as well. Yeah, you can go on. They open your microphone.
You're still muted.
Yeah. You're muted.
So, sorry, I don't want to abuse. Anyway, thank you for your kindness. So, very fast one. To lower the cost of test, or maybe to lower the cost of having a large data set to train the model, we can use simulation. Cost less than real test, of course, and then you add an uncertainty. So what about this? So can we increase the training data set with the data not from the field but from the simulation that costs much less? In which are the what is the mismatch? Or
yeah, so there's that has been attempted as well, with mixed success as well. So, you know, there's one way is there's different ways you can do this. You can either create synthetically generated data using the same type of graphics engines that video games use, and they're getting better and better and better. The jury is still out on that one. You know, how well you can transfer those situations, but certainly that's one way of doing it. The other way is to use data augmentation. So you can take real data and then manipulate that. So if you look at images, you can reverse the images, you can change the brightness, you can change the amount of noise and everything. That's been used quite heavily as well. And I think that's legitimate to do so as well. And I think what needs to be looked at in more detail, and that's really a non-trivial task, is what impact that has on the function and the ability of the function to then operate correctly with then real data during operation. But if we look back, if I just take you back a couple of slides here, what this slide is saying is actually, this is just looking at test evidence. It's saying we've got two different types of test evidence, the green and the brown here at the bottom. The green was from real data, the brown was from simulated data. And of course, we don't really trust this evidence. So after some assurance work, we've added uncertainty to this evidence, but we've still got two independent sources of evidence. And we could try to get more and more real test data, but we know we're always going to have the same types of problems. That, you know, it's never going to be a perfect coverage of our input space. There's always going to be some other types of issues. But if we can collect completely independent data, for example, using synthetic data, then at some point we can say we've got two independent measurements, we can combine those again, and we've got two different opinions, independent, and if they come to the same answer, in this case, a recall rate of around 99%, then we can trust that a little bit better. So sometimes actually adding just more and more of the same types of test data doesn't get you very far, because that test data will suffer from the same types of problems. But actually looking at independent complementary types of evidence, different types of evidence, actually gives a greater benefit. So it may be that actually, instead of just driving around in a circle one more time to collect more data of the same type of problems, actually go and looking at a different type of testing technique, a different type of analysis technique could help you to reduce the uncertainty. That was one of the reasons we were looking at these different approaches to be able to model how uncertainty in our test data can be reasoned about and combined and reduced or increased as well. So that's another way of looking at it. But there isn't a standard that tells you exactly how to do that. And one of the pieces of work we're looking at next is to say, for certain types of problems, such as image-based classification problems with deep neural networks, what would be the right combination of evidence to get to like the most efficient assurance argument? And if we were then to look at another type of problem, such as support vector machines for the trajectory planning of robot arms, we might need another completely different set of evidence to combine as well. So it is one way of looking at it. Sometimes just more of the same data with the same type of problems doesn't help you, but actually having a diverse set of evidence can actually get you farther.
Thanks a lot.
Okay.
Yeah.
Nice question.
So it can be on the right way as a driver for the verification and validation process. Yep. That's very interesting. Well, we may have many other curiosities at least, but we would like to be European AI compliant and don't. Lucanos is right. We have to close and thank again Simon. If you agree, Simon, we share here Lucanos in a kind of autonomous driving, or no, it is we share and thanks Spencer as well. Nice to have your presence in there. We share the presentation, the video to all the audience and inner networks, and we hope in other occasion to work and discuss together. Okay. Thank again, guys, and keep in touch.
Thanks for the great questions, and thanks for inviting me. Yeah.
Okay, so thank you again, Simon, for your kind and very interesting presentation. Thanks to all the audience, and we wait you for the next event of the seminar webinar series. So have a nice evening to everyone.
Okay, thank you. Bye-bye, everyone.
Bye.
Thanks, Simon.
Thank you, everybody.
Bye.
Thank you.